From flight to rest. The journey of a droplet. This video describes the pathway of airblast spray droplets from their release at the nozzle, through the air, to their rest on the target, off target on the ground, or at an off-site location. Spray. Liquid that is delivered into or driven through the air in the form of tiny droplets. Spray is liquid, not gas. Spray is liquid, only that it is disintegrated into many tiny droplets. The process of breaking up bulk liquid to produce spray is called atomization. This can be achieved when liquid under pressure exits through an atomizer. An atomizer is a device for emitting liquid as spray, a typical example used in air blast sprayers being a hydraulic nozzle. Other examples are rotary disc atomizers used in electrostatic sprayers and pulse width modulated nozzles or PWM nozzles found in some precision sprayers.
Air blast sprayers are commonly used for pesticide application in trees and vines. In conventional air blast sprayers, the spray is discharged radially along with a blast of air which carries the spray to the target. As in this simplified schematic of an air blast sprayer, the journey of the droplet begins when the pump draws spray liquid from the tank and pushes it out as spray, the process of atomization, through nozzles on a vertical or radial boom. As the spray droplets take flight, air is drawn by the fan and discharged with the spray to serve as the vehicle by which the spray droplets will be transported to the target.
The outcome of atomization, that is, the pattern of the spray, the size range of the droplets formed, and the rate of flow all depend on the nozzle emitting the spray. There are many hydraulic nozzle designs on the market for a variety of applications. Examples used in air blast application include disc and core and air induction hollow cone tips. These devices have an orifice, that is, a small opening, through which the liquid exits as spray. The effective size of the orifice determines the range of flow rates it can achieve. However, it is the operating pressure that determines the actual flow rate attained. Two general relationships exist based on this information. 1. At a given effective size of the orifice, the operating pressure is directly proportional to the flow rate, which implies that the greater the pressure, the greater the flow, and vice versa. 2. At a given operating pressure, the effective size of orifice is proportional to the flow rate, which implies that the larger the orifice, the greater the flow, and vice versa.
The spray droplets generated are spherical in shape, and so the term droplet size refers to the diameter of a droplet, which is measured in micrometer or microns. For the same volume of liquid, the finer or smaller the droplet size, the greater the number of droplets. Similarly, the coarser or larger the droplet size, the lesser the number of droplets. However, within a given spray, droplets range in sizes from finer to coarser. The term volume median diameter or VMD, a representative droplet size, is used to describe the spray quality. VMD is defined as the droplet size at which half of the total liquid volume consists of smaller sized droplets and half the volume consists of larger sized droplets. Let's assume 4 examples of spray made from the same liquid volume and consisting of exactly 4 droplet sizes. At the top left corner, each droplet size is made up of 25% of the volume, so the VMD will be a size between the middle droplet sizes. Next, on the right hand, the smallest droplet size is made up of only 20% of the volume and the next size is 30% of the volume. Therefore, the VMD is the same although the droplet size distribution is different. At the bottom left corner, the smallest droplet size makes up only 15% and the second largest size is increased by 5%. Adding the percentages, the 50% mark will fall in the second largest size. So, the VMD is greater than in the above 2 examples. In the last example in the bottom right corner, the smallest size is further reduced to 10% and the largest size is increased to 30%. So, the same VMD as the third example is attained for this spray. These examples represent how spray quality can differ among different situations.
And this is how spray quality is represented graphically, as a sigmoid curve or an S-curve. Each of these curves represents spray from a different disc core nozzle. Here, D213 is the smallest size while D646 is the largest size in terms of flow rate and droplet size. The steeper the curve, the greater the percentage of fine droplets and the smaller the VMD. On the other hand, the gentler the curve, the lesser the percentage of fine drops. To find the VMD, a horizontal line is drawn from the 50% mark on the vertical axis to touch the curve, from where a vertical line is drawn downwards to find the corresponding mark on the droplet size axis. So, increasing the nozzle size from D213 to D646 increases the VMD from about 140 microns to about 320 microns. Also, for the same nozzle size such as D425 in this example, increasing operating pressure decreases the droplet size. So, the S-curve becomes steeper and steeper as you increase the pressure from 87 psi to 218 psi.
As the sprayer travels along the drive lane, the spray is applied to the target canopy immediately adjacent to the sprayer. As the spray exits the sprayer outlet in the direction of the target, it first experiences a drastic reduction in its velocity while expanding both vertically and across its path, before dispersing along with a steady reduction in velocity. It passes through the target canopy, emerges out from the other side, and continues its journey until it is fully dispersed.
So, after a droplet takes flight from the nozzle, it will continue its journey all the way until it comes to rest. Its final resting place depends upon where it finds itself within the spray cloud. In its path, if the droplet is intercepted by the ground, it will come to rest and deposit on the ground. If it is intercepted by a leaf or branch inside the target tree canopy, it will come to rest and deposit inside the canopy. Otherwise, if it misses the canopy, it will journey on until it comes to rest on other canopies or on the ground within the application site, or it will move off-site and come to rest on the ground or any other surfaces.
But the journey from flight to rest is influenced by the droplet size. For instance, let us consider droplets falling from a height of 10 feet. A 400 microns droplet takes 2 seconds to fall from that 10 feet high, but it takes a 20 microns droplet a whole 4 minutes. Thus, the 20 microns droplet lingers in the air much longer and is more prone to drift. Now let's look at the lateral movement of different size droplets at 10 feet high. A 400 microns droplet in a 3 miles per hour wind will travel only 8 feet before making landfall. Whereas, a 20 microns droplet can travel about 1,056 feet before making landfall, that is 1/5 of a mile. This means that finer droplets can travel farther and have a greater potential to contaminate off-site locations.
In brief, after exiting the nozzle, a spray droplet may end up on the ground in the treated orchard or vineyard, on the target tree canopy or other canopies, or may travel beyond the application site and come to rest at an unintended off-site location. And from the time it takes flight to when it comes to rest, the droplet will undergo evaporation and size reduction and may become detrained from the spray cloud to deposit on the ground or drift. These processes are influenced by the weather condition at the time of application, which must be considered before the application is done. This presentation has been brought to you by the Agricultural Application Engineering, or ARGAPE, program. University of California Agriculture and Natural Resources. Kearney Agricultural Research and Extension Center, Parlier, California. With affiliation to the Biological and Agricultural Engineering Department, UC Davis. Thanks for watching.